Ever look up at the night sky and wonder what keeps a planet from just flying off into space? What keeps it locked in that perfect, predictable dance? Well, the answer is a really cool and kind of counterintuitive rule of physics. Today, we're diving into angular momentum, the secret rule that dictates everything from a simple thrown stone to the cosmic waltz of entire galaxies.
All right, let's just jump right in with a question that seems super simple, but it's actually the key to this whole thing. Imagine a rock, just flying straight through the air. It's not spinning, not rotating at all. Does it have angular momentum? Your gut probably screams, no way, how could it?
But the wild thing is, the answer is yes, it absolutely can. And getting our heads around why, well, that's the whole game today. This one idea is going to unlock how we see orbits and motion across the universe. Okay, so how on Earth can a straight line have some kind of spin? To get it, we need a little thought experiment. We're going to build this idea from the ground up, starting with that simple rock. So picture this. Our stone is zipping along, and it's about to smack into the end of a very light rod that's pinned down at the other end, kind of like a hinge. Bam! The stone hits it, sticks to it, and what happens? The whole thing, the rod with the stone now stuck on the end, starts to spin. Suddenly, it's got angular momentum, clear as day. So here's the kicker. In physics, angular momentum doesn't just, poof into existence. The only way to change it is with an external twisting force, which we call a torque. In our little experiment, there were no outside twists. All the forces were internal, just between the stone and the rod. That means if the system had momentum after the crash, it must have had it before the crash. And since the rod was just sitting there, all of that starting momentum had to belong to the stone. And this leads us to a really, really profound idea. Angular momentum isn't some property an object just has on its own. It's something it has in relation to a specific point that you choose to measure from. It all depends on your point of view. The amount of this momentum, its magnitude, is calculated with this simple formula. L equals m times v times r. Now, m is mass, v is velocity, we know those. But r is the secret ingredient here. It's the shortest possible distance, like a perfect 90-degree line, from your chosen reference point over to the path the object is traveling on. And this is huge. It means if you just move your reference point, you change that r value. And if you change r, you change the angular momentum you calculate, even though the stone itself is doing the exact same thing. For instance, let's say you're measuring from a point that's far from the stone's path. That gives you a big r and a high angular momentum. But if you pick a point that's much closer, r gets smaller, and so does the angular momentum. It's the same stone with the same velocity, but we get two different answers, all based on where we're measuring from. So let's push this to its logical conclusion. What if you choose a reference point that's sitting directly on the object's path? Well, in that case, the perpendicular distance r is 0, right? And so the angular momentum is also 0. It's like trying to open a door by pushing on the hinges. You're not going to get any rotation. Okay, so we've built up the intuition. Now let's look at the more complete, more powerful way that physicists write this down. This version captures not just the amount of angular momentum, but its direction too. And here it is in all its glory. Angular momentum, L, is a vector, and it's defined as the cross product of r and p. Here, r is the position vector pointing from your reference point to the object, and p is the object's linear momentum. That's just its mass times its velocity. This one little equation packs a huge punch. Its magnitude ends up giving us that same mvr we saw before, and its direction, which you can figure out using something called the right-hand rule, tells you the exact axis the object would spin around. It is just a beautifully efficient piece of math. So now we can take this powerful concept and apply it where it really shines, to planets in orbit. To do that, we first need to talk about torque. You can just think of torque as the rotational version of force. It's what causes something to start or stop spinning. And hey, look at that formula. It looks really similar, doesn't it? Torque is the cross product of the position vector r and the force vector F. Basically, torque is what changes angular momentum. Now here's the key. For a planet orbiting the sun, the force of gravity always points directly toward the center of the sun. This means the force vector, F, is always perfectly lined up with the position vector, R. They're anti-parallel, so the angle between them is always 180 degrees. And since the sine of 180 degrees is 0, the cross product is 0. The torque is 0. Always. And here it is,
This is the grand finale. If the net external torque on a system is zero, its total angular momentum cannot change. It is conserved. It has to stay constant. And this isn't just a neat math trick. This is one of the most fundamental conservation laws in the entire universe. It explains the beautiful clockwork-like regularity of the cosmos. Now, for a simple circular orbit, this might seem kind of obvious, but look at a real elliptical orbit. The planet's distance, r, is constantly changing. Its speed, v, is also changing. It speeds way up when it gets closer to the sun, and it slows way down when it's farther away. And this is the magic. Because the torque is always zero, the product MVR, the angular momentum, remains perfectly, unchangingly constant through the entire orbit. That's the secret. So the single most important number that explains the stability of our solar system is zero. That's the net torque, the twisting force that the sun's gravity puts on any of its planets. Zero. This principle gives us incredible predictive power. I mean, if we know a satellite's speed and distance at just one single point in its orbit, we can use the conservation of angular momentum to calculate its speed at any other point. It is a foundational tool for astronomers and aerospace engineers. So let's just recap the big takeaways. First, an object moving in a perfectly straight line can, in fact, have angular momentum. Second, that momentum is always relative to a reference point that you choose. Third, gravity is a central force, which is just a fancy way of saying it produces zero torque on an orbiting body relative to that center. And finally, because of all this, the angular momentum of an orbiting body is one of nature's great conserved quantities. It just doesn't change. This conservation law operates on every single scale, which leaves us with a final massive question to think about. If the total angular momentum of an isolated system must always stay the same, what happens to all that spin when two entire galaxies, each with trillions of orbiting stars, collide and merge?